Here's how to make a fun-sized turret. First, you're going to want to get a camera. Any camera will work as long as you know the specs.
The one I'm using is the Logitech C270.
After you acquire your webcam, you're going to import 4 Python libraries. CV2, which is going to help our script detect and track things with decent accuracy. NumPy, which is going to help us do some basic matrix multiplication, and is also what OpenCV relies on to perform lots of tasks. MediaPipe, which will detect faces and give us unnecessary information about their relative location so that OpenCV can track them. And time, so we can calculate when a face was last detected. Face detection is exactly what it sounds like. Here, I have the AI model selection, set to 0. This tells MediaPipe to use its short-range model. Min detection confidence is set to 0.5, which means any face below 50% certainty gets ignored. Lead time is a predictive lead. Basically, I'm telling the turret to aim 150 milliseconds ahead of where my face actually is to account for servo lag. If you don't know what servos are, they're basically these cute little motors that are going to make our fun-sized turret possible. Since we're working in real life and not code, we have to use degrees instead of pixels. The Logitech C270 that I mentioned earlier has roughly a 55-degree field of view. And since we want to work in degrees, we have to find the number of degrees per pixel. We can get this by dividing the camera's FOV by its resolution. With face tracking, the coordinates are rarely stationary, meaning 1 second your position could be interpreted as 100, 100, and then the next 103, 105, even though you barely moved. These are called noisy measurements. This would cause the servos to tweak out, which is bad. This is where Kalman Filtering comes in. A Kalman filter is an algorithm that estimates the true state of a moving object or system by combining a rough mathematical prediction with our noisy sensor measurements. First, we're going to create a filter with 4 state variables, x, y, the velocity of x, and the velocity of y. We're also going to have 2 measurement variables, x and y. After this, we define our state transition matrix, which we'll call f. This encodes our constant velocity motion model. Next, we need to define our observation matrix h, which maps our full 4-dimensional state vector into something we can actually measure, namely x and y. Q is our process noise covariance. It determines how much we trust our physics model. A lower value means we believe our constant velocity motion is highly accurate. R is our measurement noise covariance. It determines how much we trust the camera, which is especially relevant for the noisy measurements I mentioned earlier. P is our error covariance. It's initialized as an identity matrix to start, and it updates every frame. It represents our uncertainty in the current state estimate. The Kalman gain K balances Q and R to tell the filter how much to trust each source. A high K means trust the measurement, a low K means trust the model. Here we call predict, which projects our state forward in time using the transition matrix F. This runs every frame regardless of whether a face is detected. After that, we correct the prediction. The innovation, z sub k minus h times x hat sub k, is the gap between what the camera saw and what the filter expected. K scales how aggressively we close that gap, and p shrinks to reflect that we just got new information. The issue with this is that we're assuming every frame takes the same amount of time, which isn't true. This is where this line comes in. Here we update f every frame with the real elapsed time. This means that if frames drop, the filter doesn't hallucinate position jumps. Here we predict the future positions of x and y using some simple kinematics. After this, we calculate the number of degrees our pan and tilt servos need to move based on how many pixels the predicted face position is from the center. We multiply our angle error by 0.1 to prevent our motors from constantly overshooting and oscillating back and forth. If no face is found, we grab the prior state to allow the filter to continue coasting on its velocity model. We've made it this far, but we need hardware to continue the project. This is due to the fact that our camera can't turn, so our angle error is infinitely added to our pan and tilt positions without any recourse.
To resolve this issue, you're going to want to purchase an Arduino, a breadboard, jumper wires, 9G servos, and a pan and tilt kit to enable the turret to move like, well, a turret. Now that you've got all your supplies, the next step is to assemble the pan and tilt kit. You'd think this would be the most trivial portion. That, however, is wrong. For me at least. I'm ashamed to admit I spent 4 hours trimming plastic before assembling this monstrosity. Immediately after finishing the turret, I downloaded Arduino's IDE and configured the board I had bought so I could start writing code to tell the servos how to move. After doing this, I realized I had no idea how to get my Python code to communicate with my C++ code in the Arduino IDE. After doing a bit of research, I discovered the serial library, which would allow me to do exactly what I wanted. This line establishes a serial connection to my Arduino. Port specifies the serial port the Arduino is connected to. Baud rate sets the data transfer speed in bits per second. Timeout dictates how long the serial port will wait in seconds when attempting to read data before giving up. At the top of our Arduino code, we establish 2 servo objects. One for our pan servo, which handles horizontal movement, and one for our tilt servo, which handles vertical movement. Inside the setup function, we establish a serial connection using the same baud rate as our Python script. After that, we attach our pan and tilt servos to digital pins 9 and 10 on the Arduino to control their movement. Then inside the loop function, we read in our pan and tilt angle over serial and write them directly to the servos. Software is one thing, but now we have to set up the wiring. Servos have 3 wires. The signal wire acts as a command transmitter. It carries a PWM signal from the Arduino to tell the servo what position to hold. If you don't know what PWM is, short for pulse width modulation, it's a common electronics technique that controls power by rapidly switching a signal on and off. The ground wire acts as the return path for our electrical current, completing the circuit back to the negative terminal of the power supply. The power wire carries the voltage and current required to drive the internal motor and electronics. Before connecting our servos to the Arduino, we first need to connect the Arduino to the breadboard. We run 2 male-to-male jumper wires from the Arduino, one from the 5-volt pin and one from the ground pin, into the breadboard's power rails. This gives both servos a shared power and ground source. After this, we connect the servo signal wires to the correct PWM pins on the Arduino, pin 9 for pan and pin 10 for tilt, and plug their power and ground wires into the breadboard's power rails. Now you should be pretty much good to go. All that's left is uploading your Arduino code and running the Python script while the Arduino is connected to your PC, making sure your camera is securely attached to the turret. As you can see, I use the ingenious solution of just taping my camera down, but I'm sure you can come up with something better. I'd like to note that the term turret, which I've used throughout this video, is a bit of a misnomer. It only has the movement portion of the turret rather than any of the other features. The products and resources I used will be linked in the description or in the comments if you're watching through TikTok or Instagram. I hope you enjoyed this. This was my first attempt at actually building something. I've been doing competitive programming for around a year now, so my programming skills are much stronger than my ability to work with hardware. If you'd like to see an upgraded version of this or me building something else, let me know in the comments, and feel free to support me through my Cash App since these projects do cost money.